So we said 0.6 and 4. Agreed? Okay, so that original problem, and we graphed it, so we're cheating the system a little bit. This is the original problem, and it says to factor it. So what we did in order to cheat the system is we're using desmos to do this. And we want to see where it crosses the x-axis. Okay? Is everyone with me? So we're kind of playing with the system a little bit to see if we can make it work. Now, we have to start thinking, okay, this is x equals 4. So if that's x equals 4, the binomial that goes with it is this. And how I get that is I just basically subtract 4 from both sides. So I definitely have that for one of my factors. Okay? Now, 0.6 is the same thing as 6 over 10. Agreed? And I can reduce that to 3 over 5. You agree with that? Okay, this one worked nicely because I had a singleton decimal, so it's just, whatever over 10. Okay, this one worked nicely, but I'm going to show you if it didn't work out how to figure it out. So in order to do this, I'm going to multiply both sides by 5. So this gives you 5x equals 3. Subtract 3. So you get 5x minus 3. So 5x minus 3 and x minus 4 is the factored version of this. Okay? And it takes all the guesswork out, which is nice. But I'm just trying to show you how you can use desmos as a tool if you get hung up on the factoring. Because let's face it, factoring sometimes is not the most friendly. Okay? But I just want to show you how we could cheat the system a little bit. Now, if we didn't know, let's say this answer here came out to some big old decimal. Okay? So what that basically means is this answer is irrational. Okay? And if you remember correctly, an irrational number is a number that's a decimal that can't be written as a fraction. It's a non-terminating decimal that goes on forever. So we kind of have that. So let's see what would happen if this 0.6 didn't come out to something nice. Let's say that 0.6 came out to be something huge. But you knew this one. Okay? So what you're going to do is you're going to take this equation and your coefficients, and you're going to use synthetic division. So I'm going to divide by 4. Now this one's going to work out nice because we knew it would, but let's pretend it didn't. So then I'm going to take my coefficients. So I have 5, negative 23, and 12. I don't have any gaps. And we're going to use synthetic division. So I'm going to bring that 5 straight down. 5 times 4 is 20. Bring those straight down, so I get negative 3. That gives me negative 12. And that gives me 0. Thanks, Dan.
Yeah. I'm trying to stop him at the door.
All right, so the nice thing about this is right here. This verifies that 4 is a solution because we didn't have that. This was 5x squared, but this right here becomes 5x minus 3. Okay, it's 1 degree lower. So this would be an x and then a constant, so 5x minus 3. And again, that worked out really nicely. If it came out irrational, then this might help us to solve or might help us direct us a little bit more. But, in this class, I can't speak for other classes, but in this class, if we get stuck on a scenario that you just can't figure out how to factor it, then we have to kind of focus on it. So now, I want to look at, say, number 10. Number 10. I'm going to go on desmos with number 10. So if I graph number 10, oops. Again, I'm going to have the y equals. so I can graph it. So I get 2x raised to the third plus 9x raised to the second minus 6x minus 30. So item number 1, it's raised to the third power. So that technically means, do what? Oh, I got it. Oh, minus 5. Thank you. There we go. So it's raised to the third power. The nice thing is, if this is raised to the third power and it crosses 3 times, that's what you want. But it is possible that this graph crosses the x-axis once and never crosses it again, which means your other 2 solutions are non-real answers. Okay? So what you can do is you click on these, and we got some nice values. We have solutions of -5, -0.5, and 1. So if we wanted to write the factored version of this, well, -0.5 is the same thing as -0.5, agree? Mm-hmm. So let's go back to this right here. What were my answers? -0.5, so, and 1, okay. -5, -0.5, and 1. Okay, so each of these is going to be x equals. So if you wanted to write the factored version, bring the 5 over, so you get x plus 5. This, you need to realize it has to be converted to this. Multiply both sides by 2. Bring the 1 over. And this one, subtract the 1. So these right here, this, and this, all multiplied together, is that problem. So again, you have a valuable tool as Desmos. Now, why don't we always show Desmos? Well, unfortunately, ACT and SAT and AP haven't caught up with Desmos yet. So they say, no, they have to be able to do it on their own. The nice thing is, a lot of times when you get to college, when you're doing these kind of problems, it's make it work. Show your thought process. So it might give you some guidance of how to go through it. Now, the reason why number 8 doesn't work is you have x to the third, y to the second. You have x to the fourth, y to the third. So then that's one of the ones that you actually have to physically try and break up by factoring it. But then let's move down to say let's do number 12. Oops. Number 12. Now, friends, you could try and graph this as it sits, but it might mess with you a little bit. So what I would strongly encourage in this kind of problem to look at is take this and have y equals 2x to the third. You take this and have y is equal to 50. Now x to the third looks like this kind of graph. Or 50x is like a line that does that. So when you have a third degree polynomial and you have a linear component to it, this linear could cross our graph 3 times. It could cross 1 time. But the nice thing is it's guaranteed to cross at least once. Okay? So right now we have technically possibly 3 solutions we're looking for. We're looking for the x component of where it crosses only. We're not looking for the y component. Okay, so that's going to be number 12. So if I try and use this on Desmos, I'm going to have 2 different things I'm going to do here. I go y equals the 2x to the third. I forgot what I did. So there's our first graph, and then we have y equals 50x. So we kind of have this vertical thing, but if you zoom out enough, you're going to realize it kind of crosses twice. Now the hard thing is, you can say, okay, where does this intersection take place? And that's taking place at 0, 0, and that's fine. Okay? If you wanted to, Desmos is user-friendly enough that you can kind of just scroll with it. You can try zooming out, bring them a little closer to each other. Sometimes it gets a little tougher going, where is this going to work at? So we're looking at our 0, 0. So the x0 is our first solution. And then it looks like it's going to try and cross somewhere in here. I don't know. I can't see it. So I'm trying to get to the exact value. So now I'm like zooming in on some region that I think it's going to cross at. Maybe here. Maybe right there. So that would be at 5. It would cross at. So I took all of that to get to 5. And again, you're only looking at the exponent. But you're using the grapher to try and get you a solution. If you were to look at, say, number 15, we're going to graph y equals 4 raised to the x. And I'm also looking at y equals 51. I can't see it on my graph because I kind of blurred it. So I'm looking for the red line as well. Let's see my red line. Let's see if I can go just home. Okay, so I have that. Oop, that should be 50. There's a 51. So the y equals 51. We're going to scroll up until we find 51. So there it is. You click there. The x component is your answer, so 2.836. Okay? And again, you're not worried about the y value because you're only using the grapher to give you some indication of where to take place. Okay, so that's the front page. That's the front page. Let me flip to the back page, and I want to look at 17, 18, and 19 and doing it by hand. So you hang on to those fancy Chromebooks. So number 17, we have this. Okay, so two ways I'm going to look at this. I have -1 and I have +4. I'm just going to kind of put 2 points there and there. And we're going to call those critical values. And how I got those critical values is I took each set of parentheses and set them equal to 0. So if I FOILed out x minus 4 and x plus 1, I'd wind up with x squared, positive x squared. Agree? If it's positive x squared, it's a parabola. But notice I don't have a y-axis. So what's going to take place is you have -1 here, you have +4 here. So on this side, and on this side, if it was a parabola, we would have a positive region. And in between them, and I have a negative region, which is below. But we're trying to get you away from this to getting to this. And if you were to write the interval, being I want greater than 0 means positive. So that means from -infinity to -1, round bracket. The reason it's a round bracket is there's not an equal sign there. And then from round bracket 4 to infinity, this is the solution that they're looking for that goes with this. Okay, so you're kind of taking a two-dimensional object and you're trying to steer away from it. You're trying to find something called the critical value. And all the critical value would be where it would cross the x-axis if you had graphed it on the xy axis. And I don't know why they always go with that way. I just know that, with some calculus stuff, they like to do one-dimensional analysis using just the x-axis. and this is that up there is called a sign line. So you have plus, minus, plus. You have critical values. You know, we call these critical values CV. We abbreviate sometimes. They're critical values. That means that the graph is going from positive to negative, or from negative to positive. So that's what's taking place with critical values. Okay, and that's going to walk us into when we start getting into derivatives, but that's what's taking place. So for number 18, talk to me how you're going to do this problem. Tell me my two critical values just by looking at it. Yeah. -3 and 2, agree? And you want to make sure you put them appropriately in the number line. Don't have the negative on the right side of a positive or vice versa. So those are, if I had graphed this, that's where my parabola would be crossing the x-axis. Does that make sense? Clear as mud? If I were to start foiling this out, it would give me 2x squared, which means you're talking about a parabola that opens upward. Agreed? Which means over here and over here, you're talking about positive region. In the middle, you're talking about negative region. This means I want negative. Okay? So your interval notation here, it's going to be square bracket -3 to square bracket 2. And the reason there's a square bracket is it had an equal sign. So that interval right there tells you, hey, this is where our graph would exist being negative. If I plugged a point in between -3 and 2, if I plugged it in, it would give me a value less than 0, meaning it would be negative. Okay? So, why don't you all take the rest of the period and try and figure out these problems. If you get stuck on one, we work it next time. We'll work it next time, all right? But that's all I have for you. So try and work it, talk with each other, socially distanced. And that's the same page that's on Schoology, so that whole